Tonight, let us step softly, not into a forest or an ocean, but downwards, beneath the very floor you stand on, unveiling the mysteries. What lurks under the Earth's surface? That question is an invitation. It is quiet and enormous at the same time. Imagine for a moment, closing your eyes and feeling the reassuring weight of the ground beneath you, while your thoughts gently sink through layers you cannot see, layer by layer, like drifting down through warm, slow water. Before we go further, a small and simple thing. If you enjoy this quiet corner of science, consider tapping like or subscribing. It helps this gentle exploration continue. And now, if you are comfortable, breathe slowly and let your curiosity settle into a calm, steady rhythm. We will begin with the familiar and thin skin of our planet, the crust, and then slowly descend into what lies below. The crust is, in geological terms, the apple skin of our world. It is thin compared with what lies under it, but it is where nearly all of our lives, cities, and ecosystems make their home. Under continents, that skin can be tens of kilometers thick, often around 30 to 50 kilometers on average, though it can be thicker beneath mountain ranges. Beneath oceans, the crust is thinner, more like 5 to 10 kilometers in many places, made mostly of dark, dense basalt rather than the lighter granites that help build the continents. These are broad numbers, gentle approximations that hide a great deal of local complexity. Wherever you stand, whether on a pebble beach or in a busy street, you are standing on a surface that is only the beginning. If you picture the crust as a set of brittle plates drifting slowly over a warmer, more plastic layer below, that image will serve us well as we progress. These plates do not glide effortlessly. They jostle, collide, pull apart, and slide past each other over millions of years, the processes that give us mountains, earthquakes, and the slow rearrangement of continents. But the crust itself is more than tectonic plates and rock types. It is a mosaic of rocks, sediments, and pockets of space where water and life persist. Consider the sediments that blanket many continental shelves and river basins. Layers of mud, sand, and organic matter accumulate over thousands to millions of years, preserving the slow passing of time. Between grains of sediment, in pores and tiny fractures in rock, water moves. Sometimes it moves quickly through permeable sand and gravel. Sometimes it is trapped, slow as treacle, in less permeable layers. These pockets can host surprisingly lively communities, tiny, patient ecosystems tucked away from light and wind. Even in the upper reaches of the crust, where sunlight disappears within a few meters of soil and rock, microbes make a living. They feed on organic matter carried downwards by rain and rivers, on chemical energy extracted from minerals, or on gases that percolate from deeper rocks.
Visual metaphors help, but must be used gently. If the crust is like the skin of an apple, then the pores between mineral grains are like the little spaces where crumbs hide in the folds. Microbial life in these spaces can form biofilms, slimy communal layers where cells live together and exchange nutrients. Think of a biofilm as a microscopic condo development with apartment units in tiny crevices, each unit hosting its own small, overlapping community. These are not bustling metropolises like a city by the sea. Instead, they are slow neighborhoods with residents that live at a different pace to most surface life. Temperature is a patient, organizing force as we look downwards. Close to the surface, temperatures are shaped by the air and the seasons. Deeper still, heat from Earth's interior begins to assert itself. On average, temperature increases by something like 20 to 30 degrees Celsius for every kilometer you go down in many regions. This is called the geothermal gradient, but this is a simplification and varies widely depending on local geology, tectonic setting, and the presence of fluids. Under mid-ocean ridges, heat can be intense and density shift. Under ancient shield areas, the gradient can be much lower. For our purposes tonight, it is enough to hold the idea that depth generally brings warmth, and that warmth governs chemistry and life in quiet, patient ways. Pressure increases as well. Each meter downwards adds a little more weight of rock overhead. A fracture that looks open near the surface might be squeezed shut deeper down. Pores that hold water at shallow depths can be reduced to microscopic films at greater depths, changing how microbes can move and what energy sources are available to them. Yet life persists even when pore space is a thin, wet film clinging to mural surfaces. Let us pause at a few places within the crust where human hands have reached.
Mines, for instance, are one of our earliest and most intimate ways of touching the deep. Miners descend into shafts, sometimes kilometers below the surface, and in these dark tunnels they have long encountered pockets of water, veins of minerals, and occasionally swaths of microbial life that seem strikingly out of place. Scientists have been invited to these depths to collect samples and to listen to the conversations of atoms and molecules. Boreholes drilled for scientific purposes, oil and gas exploration, or groundwater studies are another route. Some scientific boreholes are designed with extreme care to avoid contamination, using sterilized equipment and blank controls, but contamination remains a persistent challenge whenever we attempt to sample something that has been isolated for long periods. I mention these sampling challenges because they remind us to be cautious.
When a scientist reports finding a microbe deep underground, part of the task is always to establish whether that microbe truly belongs there, or whether it arrived with the drill bit, the drilling mud, or through human touch. Meticulous methods and cross-checks help, but uncertainty is a steady companion in deep biosphere research. It is a productive companion because it keeps interpretations humble and prompts creative experimental design. The crust hosts a variety of habitats. In karst landscapes, limestone regions sculpted by dissolving water, sprawling networks of caves and conduits can form, where rivers carve subterranean paths. In volcanic regions, hydrothermal systems circulate heated water, rich in dissolved minerals, fuel for specialized microbes. Between fractures and within rock grains, tiny communities eke out an existence. In the pore waters of marine sediments, microbes process the organic detritus that falls from the sunlit ocean above. All of these niches are part of what scientists call the shallow subsurface, and they set the scene for deeper mysteries. As we reach the base of the crust, the composition subtly changes, and our descent prepares us for something different, the mantle. The boundary between crust and mantle, the Mohorovičić discontinuity, or the MOHO, is a place where seismic waves change speed and rock chemistry shifts from silica-rich crustal rocks to denser, magnesium and iron-rich rocks known as peridotite and other mantle lithologies. Imagine stepping through a doorway where the furniture is the same, but the lighting and the air pressure alter the way sound behaves. That is a gentle way to picture crossing the Moho. The crust, for all its thinness, does a great deal. It supports oceans and forests. It concentrates the elements we mine and the soils we farm. It hosts the early chapters of many biogeochemical cycles. Carbon is buried in sediments and later transformed by geological processes. Sulfur and metals are redistributed by fluids at depth. Yet, as we prepare to move below, remember that the crust is only the prologue. Under it, the mantle begins, a vast layer that behaves differently depending on depth, temperature, and timescale. Descending from the crust into the upper mantle, we enter a zone that is less familiar in everyday experience. Rocks here are still solid in the sense that they maintain crystal structure, but on geological timescales they can flow. That flow is the slow convective motion that drives plate tectonics. Imagine a very thick, hot syrup that, if given enough time and enough heat, will creep and convect. This motion is not rapid. It is patient, sluggish, measured in centimeters per year rather than meters. Yet, over millions of years, those centimeters rearrange continents. Closer to the surface, in the uppermost part of the mantle, there are regions of partial melt. These are not vast lakes of molten rock covering the whole layer.
Rather, they are zones where small fractions of mantle rock become liquid due to changes in temperature, pressure, or composition, enough melt to lubricate the ascent of magma, to form volcanic eruptions at the surface, or to create mid-ocean ridges where new crust forms. It is important to be precise here. The mantle is mostly solid, but locally and transiently partial melting occurs and plays a crucial role in recycling material between interior and surface. Convection within the mantle is driven by heat escaping from the deeper earth and by the sinking of colder, denser lithospheric material at subduction zones, where one plate dives beneath another. These subducting slabs are not simply pieces of crust, they carry with them water and volatile compounds locked into minerals. As they descend, pressure and temperature transform the minerals, and fluids can be released. Those fluids lower the melting point of the surrounding mantle, feed magmatism above the slab, and, intriguingly, provide chemical pathways that can support life in environments far removed from sunlight. Here we brush up against an important idea. The interior is not chemically inert in relation to the surface.
Deep fluids can transport carbon, sulfur, and other elements, moving them between reservoirs. The mantle may store carbon in forms such as carbonate minerals and in volatile phases, and when that material returns to the surface through volcanism, it contributes to long-term cycles that shape the atmosphere and oceans over geological timescales. These processes are slow, often taking millions of years, but their cumulative effect is profound. As we continue downward through the upper mantle, temperature and pressure rise. Minerals adopt new crystal structures to balance the increasing stresses. Some of these mineral changes are abrupt, detectable by how seismic waves travel through the Earth, and they create boundaries that help us map the internal architecture from afar. Within this layered, convecting mantle, pockets of higher temperature can cause partial melting, while cooler downwellings can convect more rigidly. The net picture is one of a dynamic interior, slow in human terms, but vigorous on the planetary stage. You may be wondering where life fits into this picture, and that question leads us deeper still. For now, hold the idea that the upper mantle and the lower reaches of the crust are not entirely separate worlds. Fluids percolating from subducted slabs, serpentinization reactions, where certain minerals react with water and liberate hydrogen, and radioactive decay, all these processes can produce chemical energy that life, in principle, could exploit. In some settings, microbes have been found in rock fractures at surprising depths, drawing on chemical energy rather than sunlight.
The mechanisms by which they obtain that energy vary. Chemosynthesis uses inorganic molecules as fuel, sulfate reducers and methanogens employ different chemical pathways to extract usable energy from rock-derived substrates. Yet here I will slow enough to let that thought settle. We have descended from the surface through the crust and into the motion-filled upper mantle, and already a tapestry of interactions has unfolded. Tectonics moves material, fluids shuttle chemical species, and energy is distributed in ways that could, and sometimes do, support life. But to understand how deep life manages to do this, we must first appreciate the microhabitats available within rock and sediment. Across the crust and into the upper mantle's accessible fractures, pores and voids, there are a variety of physical spaces where microbes might live. Some of these are centimetre-scale voids, such as larger fractures in bedrock that can hold fluid flows. Others are microscopic films of water clinging to mineral surfaces. The chemistry in these microhabitats can be radically different, even across millimetres. One rock face may be rich in sulfide minerals, another dominated by iron oxides. Microbes are, to use a human analogy, highly adaptable tenants. Their metabolic toolkit is varied. Some can breathe sulfate instead of oxygen, others can reduce carbon dioxide to methane, and some harvest electrons liberated from the decay of radioactive elements in minerals, a process called radiolysis, which slowly splits water into useful chemical components. These metabolic strategies are often slow. In some deep settings, microbial cell division may take years, decades, or even longer. Their metabolic rates can be a fraction of what we see in most surface microbes. This slow pace is not a weakness, it is a viable strategy for survival in energy-limited environments. Imagine a community where consumption is deliberately sparse, where maintenance takes precedence over rapid growth. Over geological time, such strategies have allowed life to persist in niches previously thought barren. As we push our thoughts a little deeper, it is worth reflecting on the timescales. Processes in the mantle occur over millions of years. Rock cycles, subduction, metamorphosis, and melting all operate on these extended intervals. Microbial life that persists over thousands to millions of years must be metabolically and genetically resilient in ways that challenge our usual intuitions about life's urgency. Genetic exchange, mutation rates, and evolutionary pressures in such communities will differ markedly from those in fast-growing surface populations. This is one of the reasons deep biosphere research is so fascinating. It forces us to broaden our understanding of what life can be when lived at the pace of rocks. I would like to pause now and let you hold an image, the ground beneath you as a layered book, each chapter written in different ink and on different paper. The crust is the epilogue of the first chapter. The mantle is where the book expands into a long, slow drama of heat and chemistry. We are moving through pages that are warm to the touch, not with human warmth, but with the slow energy of Earth's interior. There is, of course, still so much to explore. Beneath the upper mantle lies the lower mantle, denser, hotter, changing yet again in physical behavior. Below that is the great division between the solid silicate mantle and the metallic core. Each boundary raises new questions about physical state, chemistry, and the potential for habitability. And threaded through all of this are the itinerant pathways of fluids carrying life's raw materials, and perhaps life itself, deeper than we once imagined. For tonight's descent, we will linger at the edge of the known and the speculative. We have traced the crust in comforting detail and began to move into the mantle, where solid rock behaves like a slow, creeping fluid, and where chemical energy can be unleashed in surprising ways. The route forward will take us into realms where temperature, pressure, and time conspire to create environments very different from the sunlit world we inhabit. That is where the mysteries deepen, where microbes might maintain ultra-slow lives, where hidden water might be locked in minerals, and where the energetic breadcrumbs of radiolysis and serpentinization could sustain life removed from the surface. Let us close this segment with a quiet, observational thought. The question posed by our title, Unveiling the Mysteries, What Lurks Under the Earth's Surface, has already led us to two important insights. First, beneath our feet is not an empty, inert mass, but a layered, dynamic system of rocks, fluids, and slow motion. Second, that system provides niches, small, distributed, and often energy-limited, where life can and does persist in extraordinary ways. Both of these understandings invite patience. They ask us to replace hasty wonder with steady curiosity. We will continue this journey deeper. Ahead lie stories of microbes that survive in near isolation, of water locked in minerals thousands of kilometers down, and of the clever ways humans reach into the deep to study these phenomena. For now, rest with the sense of descent, the skin of the planet, the thinness of the crust, the slow convecting mantle, the quiet chemistry that might fuel life far beneath our daily concerns. Beyond the upper mantle, as our imagined descent continues, the world of rock and time becomes even more austere. The lower mantle begins, a vast region extending from roughly 66 to 2,900 kilometers beneath the surface. These numbers are broad approximations, meant to orient, not to fix a single universal depth. Here, pressure and temperature climb steadily.
Minerals rearrange their atomic lattices into denser forms that can withstand the crushing embrace of the deep. The motion that characterizes the upper mantle does not stop. It slows and thickens, flowing on timescales that are enormous compared with a human life. Where the upper mantle may creep on the order of centimeters per year, the lower mantle behaves like a plastic mass on a scale that folds continents and shapes whole planetary rhythms. Imagine the lower mantle as a slow-moving, incandescent glacier of rock. The flow here is subdued but persistent, driven by the same hunger of heat to escape and by the grand geometry of a spherical shell. Inclusions of cooler, sinking slabs from the surface may penetrate partway down, or stall and spread, like cold plumes buried in a hot ocean. The details of those motions are teased out by seismologists, who listen to earthquakes and to the subtle shifts of seismic waves as they pass through the planet. Those waves reveal boundaries and textures invisible to the eye, telling us patiently the story of how the Earth's interior rearranges itself. At the base of the mantle lies a dramatic boundary, the core mantle boundary. There, composition changes fundamentally, from silicate minerals rich in oxygen, silicon, magnesium, and iron, to a metallic realm dominated by iron and nickel. The transition is not merely chemical, it is a change of behavior. Where silicates can sustain complex mineral structures and host water and volatile elements, metals conduct electricity and, under motion, can generate magnetic fields. The core becomes the stage for one of our planet's most consequential properties, its magnetic shield. The outer core, the first metallic layer we meet, is a convecting, electrically conducting fluid of iron alloy. It is hot, flowing, and responsive to rotational forces. As molten metal circulates and convects, it creates electric currents. Those currents, in turn, generate a magnetic field through a dynamo process. This magnetic field extends far beyond the surface, forming a protective bubble that helps deflect charged particles from the solar wind. Without this magnetosphere, and here I lean on well-supported geophysical understanding rather than speculation, Earth's atmosphere and surface conditions would be far more vulnerable to space weather. The outer core's behavior is thus intimately linked to the habitability of our planet. Beneath the churning outer core sits the inner core,
a solid ball composed mainly of iron, held solid by extraordinary pressure despite temperatures that rival the surface of the sun. The inner core may rotate at a slightly different rate compared with the mantle, and it reveals its own subtle symmetries and anisotropies to the waves that cross it. The interplay between the solid inner core and the liquid outer core is central to the dynamo process.
The precise temperature, the exact composition, and the distribution of light elements within the core are subjects of active research. Models and measurements offer converging clues, but some details remain indefinite pending further study. If this structure, crust, mantle, liquid outer core, solid inner core, sounds forbidding, remember that it is the physics of this architecture that make Earth dynamic and alive. Plate tectonics cycles nutrients, volcanism returns deep materials to the surface, and the magnetic field preserves an atmosphere more hospitable to life than would otherwise be the case. From the point of view of life, the core's role is indirect but critical. It shapes fields and flows that protect and regulate environments where life can thrive on the surface, and, intriguingly, in the subsurface as well. Now, having traced these physical layers, let us fold back into the central mystery of our voyage, life beneath the surface. We have already seen hints: microbes and fractures, biofilms and pore waters, chemical energy from mineral reactions. But the subsurface hosts a diversity of microbial strategies that are, in many ways, strikingly different from the sun-fueled world above. To understand those strategies, we must meet the organisms and the metabolisms that enable them to persist in places of dim energy and slow time. We speak often of extremophiles, and the name can conjure images of alien microbe superheroes. Let us choose gentleness instead. Extremophiles are life forms adapted to conditions that many surface organisms find hostile: high temperatures, crushing pressures, acidic or alkaline chemistries, or severe nutrient scarcity. Within this broad label live many specialized groups, each with metabolic tricks tailored to specific environments. Thermophiles prosper where temperatures are high. Some microbes flourish near hydrothermal vents on the seafloor, where temperatures can exceed 100 degrees Celsius locally. Others live in fractured rock warmed by the deep interior, yet their optimal ranges vary. Pyophiles, sometimes called barophiles, are adapted to high pressures. In the deep subsurface, where every kilometer adds more weight of rock above, life may be compressed into microhabitats where pressures would crush ordinary cells. Chemolithoautotrophs are organisms that make their living from inorganic chemical reactions. They are the ones that, without sunlight, can turn rock-derived molecules into metabolic energy. Examples include sulfate reducers and methanogens, which use sulfate or carbon dioxide respectively as part of their chemical economy. One key chemical process is chemosynthesis. Unlike photosynthesis, which uses light energy to power carbon fixation, chemosynthesis uses chemical gradients and redox reactions, where reduced compounds, hydrogen, sulfide, ferrous iron, meet oxidized compounds, sulfate, nitrate, carbon dioxide. Microbes can harness the energy of electron transfers. Think of it as a different sort of food web, built on the electricity of chemistry rather than the electricity of light. How do these chemical energies arise? There are several important sources. Serpentinization is one. When certain mantle minerals, rich in olivine, react with water, the reaction transforms rock into serpentine minerals and liberates hydrogen. Hydrogen is a small, energetic molecule that many microbes can use as a fuel. Radiolysis is another subtle but significant process. Radioactive decay of elements in rocks, uranium, thorium, and potassium, for example, releases energetic particles that can split water molecules, producing hydrogen and oxidants. This slow chemical trickle can, over extended timescales, sustain microbial communities in otherwise sealed environments. Finally, tectonic processes bring together oxidants and reductants. Fluids that carry oxidized compounds may meet rocks rich in reduced compounds, creating chemical gradients that life can exploit. A repeated image in deep biosphere studies is that of oases within deserts, microenvironments where energy and resources are sufficient to sustain small but persistent populations. These communities are often organized as biofilms, slimy mats of microbes and extracellular polymers that stick to mineral surfaces and to one another. Biofilms create microgradients of chemistry. The outer cells might access a different suite of compounds than inner cells. In the tight confines of rock pores, such organization can be essential for survival. The pace of life in these habitats is slow. Doubling times for cells may extend from months to years, even centuries in the most energy-limited settings. Some studies suggest that microbial communities deep underground may turn over extremely slowly, with generations separated by long intervals.
This slow pace raises intriguing questions about evolution and resilience. How do genetic systems remain functional over long times? How does gene exchange occur when cells rarely meet? Some deep microbes show streamlined genomes and reduced rates of mutation, strategies that suit a life of conservation rather than rapid innovation. Others retain genetic mechanisms for repair and resilience that help them endure the wear of geological time. At this point in our descent, I would like to bring forward one of the more dramatic stories from deep biosphere research, the discovery of a surprising microbial monoculture deep within a South African gold mine. This is the tale of Candidatus desulfurotus audax veator. Discovered in fluids sampled from kilometers below the surface, this organism appeared as a near monoculture, an ecosystem dominated by a single bacterium, and it seemed to subsist on hydrogen and sulfate, employing sulfate reduction as a core metabolism. The hydrogen, researchers proposed, could be supplied by radiolysis, the slow splitting of water by natural radioactivity in surrounding rocks.
That proposition is elegant because it presents a self-sustaining micro-ecosystem in isolation from sunlight and from the surface biosphere. The discovery was not a convenience, it came from careful and skeptical science. Researchers took pains to rule out contamination from drilling fluids and surface organisms. Genomic analyses revealed a metabolic repertoire suited to an underground life. Genes for sulfate reduction, for using hydrogen as an electron donor, and for making essential organic compounds from inorganic precursors. The picture that emerged was of an organism adapted to long-term, energy-limited existence in a chemical world governed by rock and radiation rather than by sunlight. I must emphasize again, isolated yet remarkable as it is, the desulfurotus story is one strand among many. It does not imply that all deep environments are dominated by single species, nor that such monocultures are common. Rather, it provides a compelling example of how life can persist under conditions once thought untenable. It forces us, gently and insistently, to broaden our idea of what an ecosystem can look like. Linked to discoveries like this is the question of water deep within the planet. For some time, scientists debated how much water might be locked away in the mantle. Evidence has accumulated that certain high-pressure minerals can incorporate hydroxyl or water in their crystal structures. Ringwoodite, a high-pressure polymorph of olivine stable in the mantle's transition zone, can host hydroxyl groups. A remarkable find of ringwoodite trapped within a diamond, an inclusion, suggested that the transition zone, roughly between 410 and 660 kilometers depth, could store a substantial amount of water in mineral form. When this ringwoodite sample showed hydroxyl, it provided direct evidence that water, in a chemically bound state, exists at those depths. It is important to be careful with the language here. When scientists say the mantle may hold water, they do not usually mean vast liquid oceans as on the surface. Rather, they mean that hydrogen and oxygen can be incorporated into minerals as hydroxyl, or that fluid phases may exist in certain circumstances. Estimates of the total amount of water equivalent in the transition zone vary. Some suggestions propose that the reservoir may be comparable to the surface oceans in order of magnitude, while other analyses are more conservative. The point is not to assert a single figure. It is to note that the mantle participates in the planet's water cycle in ways that matter for volcanism, geodynamics, and potentially for subsurface chemistry that can support life. The existence of this deep water reservoir has consequences. When material from the mantle returns to the surface via mantle plumes or during melting induced by subduction, bound volatiles may be released.
Those volatiles can influence magma chemistry, the explosivity of eruptions, and the transport of elements back into crustal reservoirs. From the point of view of habitability, the mobility of hydrogen and oxygen at depth creates the possibility of chemical gradients that microbes might exploit, where serpentinization produces hydrogen or where radiolysis continues to supply electrons. The presence of water, whether as a film, in pore spaces, or bound within minerals, is a prerequisite for biochemistry as we know it. Our scientific reach into these hidden places depends on ingenuity, patience, and rigorous protocols. Human access is mediated by mines, boreholes, and specialized drilling programs. The Kola Super Deep Borehole in Russia, an ambitious Soviet-era project, reached depths on the order of 12 kilometers and revealed a world of unexpected thermal gradients, rock deformation, and microfossils of a geological nature. Projects such as the German Continental Deep Drilling Project, KTB, and modern ocean drilling vessels like the Japanese deep-sea drilling ship Chikyu are part of a global tapestry of efforts to probe the crust and upper mantle. The Deep Carbon Observatory, an international initiative, has coordinated research into carbon's deep cycles, linking geophysics, geochemistry, and microbiology. Sampling is a delicate business. Drilling introduces foreign fluids, powdered rock, and mechanical parts into a previously isolated environment. Contamination is therefore a central concern. Scientists mitigate this risk in multiple ways. Drilling fluids can be chosen or treated to minimize biological contamination, and sterile sampling procedures can be employed where possible. Tracers, chemical or isotopic markers added to drilling mud, help reveal where contamination may have occurred. Molecular biology techniques include the use of controls and blanks to detect DNA introduced during sampling. In some projects, core interiors are aseptically subsampled in clean rooms, and samples are immediately frozen to preserve their original chemistry and microbial content. Yet no method is perfect. The possibility of contamination is part of the interpretive framework. It compels researchers to combine multiple lines of evidence, geochemical signatures, isotopic ratios, genomic analyses, and reproducibility across independent samples before concluding that an organism is truly indigenous to a deep environment. Beyond the caveat of contamination, there are technical limits. Drilling deep is expensive, time-consuming, and risky. Temperature and pressure conditions can alter samples during retrieval. Fluids may degas or oxidize when exposed to surface conditions. Understanding these biases is part of the craft. Careful experimental design and redundant sampling help create confidence in claims. The patient, iterative approach of science has allowed the field to make steady progress despite these challenges.
Turning from methods back to meaning, we arrive at the biogeochemical roles of the subsurface biosphere. Even sparse microbial communities, when extended over vast volumes of rock and sediment, can exert cumulative effects on global cycles of carbon, sulfur, and methane. Microbial metabolism can transform carbonates, produce methane through methanogenesis, oxidize reduced compounds, and influence the mobility of elements that are relevant to both climate and geological chemistry. How large these effects are, whether deep microbes contribute substantially to global fluxes or act more as local modulators, is an active area of study. Estimates of the biomass and activity of the deep biosphere vary widely. Some studies suggest the subsurface could match or even exceed surface biomass in certain metrics, while others are more cautious, highlighting uncertainties in scaling local observations to planetary volumes. The honest scientific posture is restraint. Numbers are proposed with acknowledged ranges and caveats. There are also practical applications that flow from studying deep life. Enzymes from thermophiles have already entered industrial use. Thermostable polymerases revolutionized molecular biology once they were discovered. Enzymes that work under high pressure or that catalyze reactions in low-energy settings may have future biotechnological relevance. Microbes that can leach metals from ores, bioleaching, are part of an established mining practice in some contexts. Bioremediation strategies draw on microbes' abilities to transform pollutants into less harmful forms. At the same time, the manipulation of deep systems must be approached carefully. Perturbing geological or microbial equilibriums without understanding their broader impacts could have unforeseen consequences. We now broaden our gaze beyond Earth. What does the subsurface tell us about the possibility of life on other worlds? The analogy is tempting and reasonable. Where there is chemical energy and liquid water, life as we understand it could, in principle, find a niche. Mars has subsurface ice, and there is evidence of past hydrothermal activity. Beneath the icy crusts of Europa and Enceladus, global oceans may interact with rocky mantles, potentially producing serpentinization and chemical gradients. In those settings, chemosynthesis could be a plausible foundation for ecosystems. Venus, with a surface hostile to life as we know it, may nonetheless have temperate conditions in its lower atmosphere or in deep subsurface environments, though such possibilities are more speculative. Yet we must tread here with scientific humility. Analogy is not proof. The mere presence of ingredients does not guarantee life's emergence. Planetary history, energy fluxes, and a host of contingencies matter. When we speak of Mars or Europa, we frame the discussion as a reasoned possibility supported by analogies on Earth, not as a prediction. The best approach is to use what we learn here to design careful missions and instruments that can test hypotheses on other worlds with rigor. There are further philosophical ripples from these discoveries. The fact that life persists in pockets beneath the surface, in slow, patient communities that persist on the chemistry of rocks and radiation, invites us to reconsider what life needs and how resilient it might be. It teaches humility about our anthropocentric timelines and about the assumption that life must be fast and visible to be vital. The deep biosphere is a study in patience. It is a reminder that ecosystems do not need to be dramatic to be consequential. As we near the end of our descent and begin the gentle ascent of thought, it helps to reflect on temporal scales again.
When microbial generations are measured in decades, and when tectonic cycles measure millions of years, we confront a temporal mosaic in which life and geology entwine. Evolutionary processes in the deep may be slow, but they are not static. Genetic novelty can arise, be preserved, and when conditions change, be drawn back into more active ecological roles. The deep is both archive and active participant in Earth's biography. So what now do we say in answer to our guiding question? Unveiling the mysteries, what lurks under the Earth's surface? The truthful, calming answer is layered. Beneath us lies a structured planet of crust, mantle, and core, each layer with its own chemistry and motion. Within that physical architecture, there are niches, fractures, pore films, hydrothermal veins, and mineral-bound spaces that host life. That life is often slow, adapting to limited energy, and drawing from rock-driven chemistry, hydrogen from serpentinization or radiolysis, sulfate and carbon dioxide reshaped into metabolic energy. We have found examples of remarkable adaptation, microbial communities at surprising depths, organisms like Candidatus desulphorutus audax veator that hint at self-sustaining subterranean ecosystems, and mineral inclusions like ringwoodite that suggest water exists far below the seas we know. But the mysteries are far from all solved. The scale of subsurface biomass, the exact nature of deep water reservoirs, the full diversity of deep metabolisms, and the role of subsurface processes in global cycles remain active fields of research. Estimates and models continue to be refined. New drilling projects, improved contamination controls, and interdisciplinary studies that bridge geology, chemistry, and microbiology will continue to reshape our understanding. And as they do, they will likely reveal more subtle, patient worlds tucked into the planet's fabric. There is a practical, human side to all this, how our knowledge can be used and how it should be stewarded.
Deep subsurface research can inform responsible resource extraction, help develop biotechnologies adapted to extreme conditions, and perhaps even guide the search for life beyond Earth. At the same time, it compels caution. Disturbing deep microbial ecosystems or chemical equilibria without understanding their roles could produce unintended effects. Science, in its gentlest form, invites careful curiosity and measured action. Before we close, let us return to a simpler image. Picture again the ground beneath your feet. Think of it not as inert dirt, but as a multi-story house of quiet activity. The upper floors are familiar: soil life, roots, the bustle of surface ecosystems. Deeper down are rooms where time moves differently: polite, slow, deliberate movements of fluids and rocks, and small communities of life that have learned to budget energy across centuries. Deeper yet is the engine room, the mantle that flows like warmed syrup, the core that spins metal and feeds the magnetic cocoon around the planet. Together, the house is the whole. Together, these layers influence the air you breathe and the climate outside your window. If you have lingered with me through this descent, thank you. There is a particular kind of contentment in quietly recognizing how much goes on, unseen, under our feet. The mysteries we have examined are not mere curiosities. They are parts of a living planet, complex and interdependent, revealing that life can find purchase in places that at first glance seem inhospitable. If this slow journey pleased you, and if this quiet corner of science helps you feel both curious and soothed, I would be grateful if you considered subscribing to join future nightly dives, and perhaps share where you are listening from. It helps the channel gently keep going, and it lets me know which quiet rooms of the world are listening. Now, as we close this descent and allow our thoughts to drift upward toward the surface and the small, steady pulse of life we know well, rest with the image of the planet as a patient keeper of secrets. Unveiling the mysteries, what lurks under the Earth's surface? We have seen that beneath our familiar ground, there is a vast, slow world, warm, pressurized, chemically alive, that reshapes our sense of habitability and resilience. Let that thought settle beside you like a soft blanket. If sleep is your companion tonight, may the quiet complexity of the deep cradle you. If curiosity still stirs, hold the question gently. There is always more to discover, slowly and patiently, underfoot.